Hello friends, I am Dr. Sangeeta Patil, Assistant Professor in the Department of Electrical and Electronics Engineering, MIT School of Computing, MIT ADT University. Welcome you all for a course on basics of transformer. Let us start the lecture.
So let us start with the ideal transformer. So what do you mean by ideal transformer? Actually, ideal trans in actual practice there is no transformer which is ideal. However, the concept of ideal transformer is very useful in designing or developing the step by step the theory of the practical transformer. So what is ideal transformer? Ideal transformer is a transformer which is having permeability of core high. It means that only negligible current is required to establish the flux in the iron core. That is the first assumption to study the ideal transformer. Second assumption is that there is no magnetic leakage. There is no magnetic leakage. It means that all the flux is confined to only the iron core and links with the both windings, primary as well as secondary. Then third assumption is that the windings have no ohmic resistance. The winding have no ohmic resistance. So these four assumptions will help us to develop the idea of the ideal transformer. And fourth assumption is that it has no losses. It has no losses. It means its efficiency is 100%. As I have told you, in practice it is not possible to have such ideal transformer. However, the concept of ideal transformer is very useful in delivering step by step the theory of the practical transformer. That's why instead of directly going to the practical transformer, first of all we'll study the ideal transformer. So let us consider the A part, that is the ideal transformer on no load. So I have drawn the schematic of the transformer here. Now let the transformer shown in this figure A is an ideal transformer. So when the primary winding of this transformer is connected to the AC voltage V1 with the secondary winding open circuited, it draws negligibly small amount of magnetizing current which is denoted by I magnetizing here. If the transformer is truly ideal, this magnetizing current would be zero. But let us say that very small current is required to establish the flux phi in the transformer. So this current is purely reactive current. Because your primary winding has no resistance, we have assumed here windings have no ohmic resistance, means my primary winding is totally or purely inductive winding. So this I magnetizing current will lag the voltage by 90 degree. And this I magnetizing current, which is very negligible, is responsible for establishing the flux phi in the core, which is in time phase with it. So let us side by side draw the phasor diagram. So what is the reference vector? What is the quantity which is applied to the primary winding? It is the voltage. So let us the voltage. I will take voltage as a reference vector. So V1 I have taken as a reference vector. When I have applied voltage across the primary winding, very small current I magnetizing will flow through the primary winding so that the flux phi will be established by it. So that current, as the primary winding have no ohmic resistance, that current will lag the voltage by 90 degree, lags the voltage by 90 degree, and this current only responsible for producing the flux, and that flux is again in time phase with the magnetizing current. So flux produced is in the time phase with the magnetizing current, because it is obvious that if there is no magnetizing current, the flux would be, there would be no flux, or flux will be zero. Now let us we have assumed that this current is very small, which set up the flux phi. So this flux induces E1 of self induction in the primary winding, which will counterbalance your applied voltage V1, and it also induces the EMF E2, which is of mutual induction in the secondary winding. So the magnitude of E1 and E2 both are proportional to the number of turns of primary and secondary winding respectively. Yesterday we have seen, or in my second lecture. What is E1? E1 is nothing but 4.44 phi m f N1. So E1 is directly proportional to N1, and E2 also directly proportional to the number of turns on the secondary winding. So the magnitude of E1 and E2 are proportional to number of turns on primary and secondary winding respectively. These EMFs lags the flux by 90 degree. How they will lag? I will tell you. Just I will draw first of all E1 and E2 vector so that I can show it here. So this is your E1, EMF of self-induction induced in the primary winding, and this will be E2. Now let us see why these EMFs lags the flux by 90 degree. These are lagging to the flux by 90 degree. This is also 90 degree. Students, we have seen that what Faraday's second law said. The magnitude of EMF is directly proportional to the rate of change of flux linkages. Right? As this flux is alternating, I can write down this as minus n d by dt of phi m sine of omega t. Right? So what I will get here? It is minus n omega phi m cos of omega t. Right? So this I can write down as n omega phi m sine of omega t minus pi by 2. Right? Holds. If I am taking voltage as a reference vector, so this is your EMF. Now with respect to current, this EMF, this minus sign indicate that it lags. It lags the flux. This is your flux. So EMF lags the flux by pi by 2. This is written with respect to the flux. So this pi by 2 means by 90 degree. Minus sign indicate that it lags. Therefore, E2 and E1 both lags the flux phi. Since the secondary circuit is open, my secondary terminal voltage V2 is nothing but approximately equals, not approximately, they are actually equals to V2 because my secondary is open circuit. So whatever the EMF induced here, that EMF is nothing but equal to the voltage across the output terminals. That's why I have written E2 is equal to V2 here. Also there being a negligible voltage drop in the primary also. Right? So there being a negligible voltage drop in the primary winding, the primary voltage V1 is equal and opposite in phase to the EMF E1 induced in the primary winding. That's why V1 and E1 both are again approximately equals, but both are opposing each other in accordance with the Lenz's law. Because what Lenz's law said? The direction of EMF is such that it will oppose the cause. So who is responsible for producing the E1? The applied voltage V1. That's why V1 will oppose the E1. So I can write down it as V1 is equal to minus E1 or E1 is equal to minus V1. So E1 is directly in phase opposition with the V1. So this figure, this is your figure number B. So this figure B shows the necessary phasor diagram for the ideal transformer under consideration when there is no load connected across the secondary circuit. The flux phi being common to the both winding, it is considered as a reference vector while drawing the phasor diagram for the practical as well as ideal transformer on the load. So here I have explained you the ideal transformer phasor diagram on no load. Now let us start with the phasor diagram of the ideal transformer on load. So come to the ideal transformer on load. So again this is the schematic of the elementary transformer drawn for understanding, and here what is the difference between previous figure and this figure? Here I have connected the load. That's why this is the ideal transformer on load. Across secondary I have connected the load. Suppose if the load having the infinite impedance is connected across secondary terminal of the ideal transformer, the current I2 starts flowing through the secondary winding. Because your circuit gets closed, that's why current I2 starts flowing through the secondary circuit. Now if I consider a general case of an inductive load having lagging power factor cos of phi 2, the current I2 lags V2 by an angle phi 2. Right? So let us now develop the phasor diagram. Again what I will take voltage as a reference vector. Wait students, I will take voltage as a reference vector. First of all, some current is taken which is called as I magnetizing, which is same as that of your previous case. This I magnetizing will produce the flux which is in time phase with it. Right? Now, when the current is circulated in the secondary winding of the transformer, according to Lenz's law, the secondary current I2 will oppose the cause of producing it. Hence, it opposes the magnetic flux. Right? So, in doing so, when my I2 is opposing the cause of producing it, this effect of opposing by I2 is nothing but the demagnetizing effect of the I2. And due to this demagnetizing effect, the flux is weakened and it reduces the amount of the self-induced EMF E2. Now when current I2 is circulated, what is the nature of this current? The nature of this current is alternating. So this alternating current will produces the alternating flux, which again link with this secondary winding and also this primary winding. Right? So let the flux produced by the I2, current I2 in the secondary winding is phi 2. So the blue dashed line shows you the flux produced by the current I2 which is circulated in the secondary circuit. Okay. So due to the current I2, flux phi 2 is produced. Initially only phi is there. Now my phi 2 will be in this direction. My phi 2 will be in this direction and phi will be in this direction. So both fluxes are opposing each other. What is effect of such fluxes? The effect of such fluxes is that your E1 will get reduced. And due to reduction in the E1, the difference between the applied voltage and the EMF induced in the primary E1 increases. And hence additional current I2 dash, which is called as load component, flows in the primary winding. So in addition to your I magnetizing, the current I2 dash, which is also called as the load component, flows through the primary winding, and that load component I2 dash will produce the flux phi 2 dash, which is shown by the black line here in the direction which is opposition to that of your I2. So this phi 2 and phi 2 dash will get cancelled with each other, and the flux in the transformer core is constant. So the magnitude of this current I2 dash is such that the demagnetizing MMF, what is the MMF? Product of turns and current. So the demagnetizing MMF, what is demagnetizing MMF? Who is producing demagnetizing effect? Your I2. So what is the demagnetizing MMF? N2 into I2, because it is circulating through the secondary winding, right? So the demagnetizing effect of this current is nearly neutralized by the primary MMF, which is equals to N1 I2 dash. N1 I2 dash. So I can write down here my N2 I2 equals to N1 I2 dash. What is I2 dash? I2 dash is nothing but additional current drawn by the primary winding, which is also called as load component, which will neutralize the MMF produced by the secondary current, right? Produced by the secondary current. Hence, from this equation, I can write down I2 dash equals to I2 into N2 by N1. N2 by N1. But students, in last lecture only we have seen what is N2 by N1. N2 by N1 is nothing but K. So I2 dash is equal to K into I2. I2 dash is nothing but K into I2. Okay. So this current I2 dash is always in anti-phase with the current I2. So what is this? This is your V1, which is taken as a reference factor initially when voltage is applied to the primary winding. I magnetizing is taken, which lags this voltage by 90 degree because winding has no resistance, and the flux produced by this current is in phase with the I magnetizing. This flux link with the primary as well as secondary winding and produces the EMF of self-induction in the primary and mutual induction in the secondary. So this is your self-induced EMF in the primary, and this is your mutual induced EMF in the secondary. Now, as there are no losses, we have said E2 is approximately equals to V2. What assumption we have made in the ideal transformer? There are no losses. So my E2 is equal to V2, right? So, but student, we have assumed that inductive load we have considered that the load which is connected across this is the inductive load. It is a inductive load. So the current of secondary lags the voltage by some angle. So this is your V2. So my current I2 of the secondary winding lags the voltage by some angle phi 2. So this is your I2, which is lagging to the V2 by angle phi 2. Okay. Now, from this equation, what we have said? The load component which is drawn by the primary current to overcome the demagnetizing effect of your load current I2, primary will draw some extra amount of current from the supply to satisfy the load requirement. And this current is in phase opposition with the I2. So I will draw I2 here, which is in phase opposition to the, so this is your I2 dash. What is I2 dash? It is nothing but the load component of the secondary current. Now there are two currents in the primary. So the current in the primary, let it be I1. It is nothing but vector sum of your I magnetizing and I2 dash. So simply I will take the vector sum here To take the vector sum, I will draw one vector in parallel with the I magnetizing of the same length. Similarly, I will draw one vector from this tip which is parallel. So this is your parallelogram, and vector sum of these two is nothing but your primary current I1. So this is your I1, which is nothing but vector sum of, this is your I magnetizing. So this is also I magnetizing. Okay. Now what is angle between V1 and I1 is nothing but your phi 1, and cosine of phi 1 is nothing but the power factor of the primary, right? So due to the load on the secondary side, the primary current of the transformer increases to supply the additional power to the load, or we can say that on application of the load, which enables the primary to draw more power from the line to meet the increased demand of the load which is connected on the secondary side. So when the transformer is on load, the total current I1 in the primary is the phasor sum of I2 dash and I magnetizing, and phi 1 is the phase difference between the V1 and I1. Hence the power factor of the primary side is, what is the power factor of primary side? It is cos of phi 1. That is cosine of angle between V1 and I1. V1 and I1. So students, on load also the flux in the transformer remains constant. Flux in the transformer remains constant. I hope that you have understood the ideal transformer on load and how flux is remaining constant and how to draw the phasor diagram of the ideal transformer on load. Now let us start with the practical transformer. Practically, it is not, in actual practice, it is not possible to have a ideal transformer without any resistance of the winding, without any leakage flux, without any losses. So above discussion, whatever the discussion that I have made previously, it is entirely based upon the ideal transformer having no core losses, no winding resistances and magnetic leakage. Now we have to take into account the effect of these factors while analyzing the behavior and performance of the transformers which are used in the actual practice. So students, I will cover the practical transformer phasor diagram on no load and load in my next lecture. Before going to that, let us study what are the different losses in the transformer. We have seen that in ideal transformer, there are no losses. There are no losses. And that's why in the phasor diagram, I have written V2 is equal to E2. But in practical transformer, there are some losses. So, what are the losses in the transformer? Losses in transformer are normally of two types. Copper losses, which are denoted by lead, they are denoted by PCU, and iron losses Let us denote the iron losses by P. Losses is nothing but the loss of power, that's why they are denoted by P suffix, Cu for copper losses, I for the iron losses. So first of all, let us see the copper losses. Let us see the copper losses. The total power loss taking place in the winding resistances of a transformer is nothing but the copper losses. Therefore, I can write down here copper loss equals to power loss in primary resistance plus power loss in secondary winding resistance. So mathematically I can write down this as copper loss is denoted by PCU equals to, we know that current taken by primary is I1 square R1, and copper loss in secondary winding is I2 square R2 watts. Where this I1 square R1 is nothing but power loss taking place in the primary resistance R1, and I1 square R2 is nothing but the copper loss taking place in the secondary resistance R2. Normally the copper loss should be kept as low as possible to increase the efficiency of the transformer. To reduce the copper loss, it is always essential to reduce the resistance R1 of the primary and R2 of the secondary winding. As it depends upon the current, this loss depends upon the current, this copper loss is also called as a variable loss. This copper loss is also called as a variable loss. And as this loss is dependent upon square of the load current, the relation between the copper loss at full load and that of half load will be different, because at full load my current will be more and at half load it will get half of that of your full load current. So PCU at half load, HL means half load, is nothing but 1/2 whole square PCU full load. So it is nothing but PCU full load upon 4. It means that at half load copper loss is reduced by 1/4 of that of your full load copper loss. Why it is like this? Because it depends upon the square of the load current. That's why this relation will come into the picture. Okay. Now the second type of loss is nothing but the iron loss. Second type of loss is nothing but iron loss, or I can say iron losses, which is denoted by Pi, So iron loss Pi is the power loss taking place in the iron core of the transformer. That's why it is called as a iron loss. It is equal to sum of two components called as hysteresis loss and eddy current loss. So I will write down here my Pi is nothing but equals to hysteresis loss plus eddy current loss. So let us first of all see what is hysteresis loss. Hysteresis loss takes place in the magnetic material. So the area enclosed by the hysteresis loop of a magnetic material represents the hysteresis loss of that particular material. In order to reduce the hysteresis loss, we have to use special magnetic material. So to reduce the hysteresis loss, what we have done? We have used the silicon steel, which is having high permeability and low reluctance, and this will reduce the hysteresis loss. Your silicon steel is a soft magnetic material, and we have seen that the soft magnetic material is having less hysteresis loop area, hence less hysteresis loss. So the magnetic material such as silicon steel has hysteresis loop with very small area, hence such materials are normally preferred for the construction of the core. But commercially such steel are also called as loaves. Such steel are also called as loaves. Means low hysteresis. Loaves means low hysteresis material. The material having low hysteresis loss. Low hysteresis loss. The hysteresis loss is normally frequency dependent. As we increase the frequency of the operation, the hysteresis loss will increase proportionately. This loss takes place in the transformer core because that transformer core is continuously subjected to the rapid reversal of the magnetization by the alternating flux which is produced by the alternating current flowing through the primary winding as well as the secondary winding. So normally the hysteresis loss is denoted by pH and it is given by KH Bm raised to 1.6 F V holds. All this you have studied in material science. So pH is nothing but equals to KH Bm raised to 1.6 F into V. So what is F here? F is nothing but the frequency. This is nothing but your frequency. What is Bm? Bm is the maximum flux density. Maximum flux density. What is this small v? Small v is nothing but volume of the magnetic material. Volume of magnetic material in meter cube. In meter cube. And KH is nothing but the hysteresis constant. KH is nothing but the hysteresis constant. Now, the second loss is nothing but the eddy current loss. Second loss is nothing but eddy current loss. If I am making the iron core of solid material instead of laminating structure, then what will happen? Area of cross section will increase. If area of the cross section will increase means resistance or opposition offered to the flow of eddy currents will be reduced. So eddy current loss will be more. So due to time varying flux, there is some EMF induced in the transformer core also. This induced EMF causes some current to flow through the core body, transformer core body. And these currents are called as the eddy currents. As the core is made up of the steel, it has some finite resistance. Hence, due to the flow of eddy current, heat will be produced. So the power loss which is there due to the eddy currents is called as eddy current loss, and that eddy current loss is given by eddy current loss which is equals to PE, which is equals to eddy current square, because obviously these currents are producing the heat in the transformer core. Eddy current square into small r. What is small r? This small r is nothing but resistance of the core. Resistance of the core. So the eddy current losses are normally minimized by using the laminated structure, and core is manufactured as a stack of laminations rather than going for the solid iron core. These laminations are insulated from each other by means of a varnish coating on all the laminations. Hence, each lamination will act as a separate core with small cross-sectional area, and that lamination will provide large resistance to the flow of the eddy current. So this PE, the empirical formula for this PE is nothing but KE Bm square F square T square and V holds. V holds. What is Ke is nothing but eddy current constant. Eddy current constant. What is Bm is the maximum flux density again. F is the frequency and the new term here is nothing but the thickness of lamination. Thickness of laminations. V is the volume of the magnetic material in the meter cube or in the cubic meter. The eddy current loss is also frequency dependent as that of your hysteresis loss. It is directly proportional to the square of operating frequency. Hence, from above two equations of eddy current loss and hysteresis loss, we have seen that iron loss Pi of the total loss component is dependent on the frequency, but copper loss is constant irrespective of frequency. Copper loss does not depend upon the frequency. So both these losses are reduced by choosing the silicon steel having small values of Kh and Ke. What is Kh? Hysteresis constant. What is Ke? Eddy current constant of the material, and by using the laminated construction for the core. Right? So in next lecture, I will cover the practical transformer. How there is a practical transformer which is having the resistance to both winding. There are core losses in both the winding. So how there is an effect of these losses as well as resistance and leakage reactance of the winding on the performance of the transformer. So thank you student for your patience listening. If you like this lecture, please don't forget to like, share and subscribe to my channel. Thank you.